In this video, we're going to look at the graphs of sine and cosine functions. So we're going to generate the graphs from the unit circle, and then we're going to identify the properties of these, what we call periodic functions, such as the period of the graph, the amplitude, the mean position, and then finally we're going to look at some of the other properties and that they have in terms of their symmetry and classify them as odd and even functions. So let's start with the sine function. So we're going to graph sine of theta. Now they're actually using, in this little interactive, they're using alpha as the angle. And so what I'm going to do is I'm going to drag this angle across, and you can see that it makes the point on the unit circle move around, and therefore it changes its x coordinate and its y coordinate. So the y coordinate of this point here is the value of sine. Okay, and so you can see that the y coordinate you could represent as a distance by this red line here. And so what we're going to do is for each angle, and they happen to be in degrees, for each angle we're going to plot on this graph over here what that particular value is. And so let's turn it on, and away we go. So we'll go back to 0. And you can see as I'm moving it, you can see the points generating as we go around, all the way up to pi on 2, or 90 degrees. And then as we come around, the position of point P is falling towards the x-axis, so the y value is getting smaller until the y value for that point, the y coordinate is 0. Then our y coordinates are negative, all the way down to a minimum value of -1 when it's 3 pi on 2, or 270 degrees. And then as we rotate back further around towards 360 degrees, or 2 pi, the y coordinates get smaller and smaller, closer to 0. And that makes our sine curve. And the reason that a sine curve or a sine function is referred to as a circular function is that it's generated from the unit circle. So as you could see, as we rotated around and around, there's no reason why we couldn't continue to rotate round and continue this graph on further. And if we did that, and we can't do that because this thing only goes to 360 degrees, if we did that, we would continue our graph up to 1, and then down to 0 for sine, and then down to -1 and back up. And we could do that infinitely. We could also measure in the opposite direction. But let's just focus on this little section of the graph for a minute. So here's a closer view of our sine function, and this time you'll notice that I've got x as our variable, and I've got x on the x-axis, and we're looking at f of x, so the function of x. Okay, so for this particular function, which goes this way, our maximum value of sine of x is our maximum value for our function, which is our maximum y value, which is this value here, which is 1. And coming down this way, our minimum value is -1. The mean value for the function is the value that's halfway between the maximum and the minimum. Because the function's symmetric, this half here for the y values, if you added it together to the y values for this half, they add up to give you this y value here. And so that y value there, where the graph is halfway above and halfway below, that's called our mean value or mean position. So our mean value or mean position is, in fact, for this graph, 0. Now, the amplitude of the graph is the difference between the mean value and the maximum, or the mean value and the minimum. And it's a distance, so it's always going to be positive. And so this value, this distance here, is our amplitude. So our amplitude for this graph is 1, a distance of 1. Okay, so next thing we're going to look at is the range for our function. And so the range is from the lowest y value to the highest y value So our range for this function includes -1 and 1. The domain for the function is, in this case, simply from 0 to 2 pi for the graph that we've drawn. But as I mentioned before, this graph could continue on in this direction and in this direction. And so our domain for our function, our maximum domain is in fact real numbers. Now, the length of the pattern over which the pattern repeats itself from beginning to end. So this is one complete pattern up to here. So this distance here, which is 2 pi, is called the period. And that is the distance that it takes for the graph to start to repeat. So our period for this graph is 2 pi. And if you like to think of it in terms of the dot going around the circle, then it's how long the angles that you need to go through to get back to the start, one complete cycle, and start again. So from here, measured in radian angles all the way around, that is 2 pi. So here's a graph that I produced on my CAS calculator. To make it show radians on the x-axis, what I did was I double-clicked on the x value and then replaced it with pi on 2, and then the rest of these values popped up. You might have to zoom in a little bit to get them to pop up, but you'll actually see that it measures it in radians and it sits the graph perfectly over with a maximum of 1 at pi on 2, 0 at pi on pi, etc., etc. Now, to measure one period on this graph, people think that you need to start at 0 and measure out to 2 pi and say that that's actually a period, but you can in reality start from any part of the pattern and find its repeating point of the pattern, and that distance there will in fact be a complete period as long as you match the next matching piece in the pattern. So I could even start from a point here and then come back and find the same matching piece over here. If I went in the other direction, the matching piece is here, the matching piece of the graph is here. So each one of these points here is one period. 1 period or 2 pi. Same with that one, same with that one. So this time we're going to generate the cosine function, and I'm going to move the little point around the unit circle, and you can see it rotating around. And this time we're looking at the length of the blue bit. So we're looking at the x coordinate for this point, and the x coordinate for this point here is the same value as that distance there. So as I go around, as we start from 0, you can see that the cos value starts at 1 and gets smaller and smaller to 0. Out the other side it becomes negative, etc., etc. So let's get it to draw this thing as we move around. So let's go back to 0. And round we go. And you can see the graph of the cosine function against the angle that we're going through. As the angle changes, the cosine value changes until we get our cosine function graph. So again, the maximum value for f of x is 1. And we've got 2 points for it here on our graph. The minimum value for cos of x is -1. For this one, the mean value, which is halfway between the maximum and the minimum, is 0. And so that's our line along here. The amplitude is the difference between the maximum or the minimum and the mean value. So our amplitude is 1. Our range is again the smallest y value, which is -1, to the largest y value, which is 1. Maximal domain is again R, because even though we have only one cycle here, it's possible to repeat the cycle over and over. And the complete length of one cycle, or our period, the complete length of one cycle is 2 pi. And if we look at the graph of the function extended to the right or extended to the left, continuing our pattern, this is what it looks like on our CAS calculator. And because the pattern repeats over and over and over, we call it a periodic function because it has a period that repeats over and over. It's called a cyclic function because it cycles between up and down and up and down. The other connotation of the word cycle means circular, to do with circles. And you can see that this particular graph here, if you think about how we made it, actually is generated from a circle. So the last thing to look at is whether these graphs are odd or even functions. So back in chapter 1, they looked at odd and even functions in terms of classifying them based on what happens to the function when you substitute in -x. What kind of graph do you get out? What's the relationship? For odd functions, you get out the negative value of the value that you get when you substitute in just x. For even function, you get just the value of the function if you substitute it in just x. So let's have a look at these in terms of sine function and cosine function. So we're going to use Tim Brzezinski's interactivity here on GeoGebra. If you want to have a look at it, you can just go to GeoGebra, pop in this code here, and it'll bring it up and you can have a play for yourself. But what I want to do right at the minute is I want to move this point here to somewhere other than pi on 2, because it's fairly obvious, somewhere in here, and then show you how the relationship is between f of x and f of minus x. Okay, so let's just move this back to about here. And then what we're going to do is we're going to look at, there's our x value there, the blue x value. So we've gone across x. And now that distance up there to the white dot is in fact the value for sine of x. Now, if I take the x value, the distance I've come across in the positive direction, swing it around to the other side. So now I've got negative x. So if I substitute in negative x, I get the value of negative sine of x, which is, if I pick up that sine value and move it across, exactly the same. So what we've got here is that sine of negative x is in fact the negative value of sine of x. And so y equals sine of x is in fact an odd function. So this is another of Tim's interactivities. So we're going to have a look at the relationship between cos of x. Let's just use that particular white dot value there. And so there's x, that's the value of cos of x. So now if I take that x value and I turn it to become negative x, what you find is that you get the same answer, cos of x. And so what we've got here is that cos of minus x is equal to cos of x. And so cos is a even function. And so finally, let's look at the relationship between sine of x and cos of x. So I've got the sine of x graph at the top, the cos of x graph at the bottom, and my dodgy colouring in over the top of sine of x. Now what I'm going to do is I'm going to pick up that line and I'm going to move that line. See me moving the line across. You can see if I move the line across and I move it across that distance, so I started there and I went to there, and that distance there is pi on 2, that what I've got is in fact the cos curve. So the cos curve here, why isn't this working? There, that bit there exactly fits this bit here. And so what I actually have is that sine of theta minus pi on 2 is equal to cos of theta. And the other thing that I can do is if I pick that line up and I move it back now and I go pi on 2 in the other direction, I have an inverse cos graph. See, it's the flipped over version of a cos graph. And if I continue this way, there's a cos graph again. So by repeatedly moving it in multiples of pi on 2, I can generate the cos graph. So there's a relationship there. And I can do the same thing here with my cos curve. If I pick up my cos curve and I start at this point here and I move it pi on 2 this way, then what I end up with is, of course, the sine function. So in summary, the sine curve looks like this, the cos curve looks like this. The maximum value for sine and cos is 1, and the minimum value is -1. That makes the range of each of these functions from -1 to 1. The mean value is the middle value between the maximum and the minimum. So for both of these functions, the mean value is 0. The amplitude is 1 and the period is 2 pi. You can use symmetry to work out the other x-intercepts for the functions. So for the sine value, the intersection point in the middle is halfway between 0 and 2 pi, so that's pi. The maximum value that's at 1 is halfway between 0 and pi, so that's pi on 2. The minimum value is halfway between pi and 2 pi, so that's 3 pi on 2. Just put it at the top because I can't fit it in. And the same thing works for the cos value. Halfway is pi, half of pi is pi on 2, and this is 3 pi on 2. You need to be able to draw these graphs by heart in exam 1. In exam 2, you can have a picture there to help you. We also know that sine is an odd function, so that sine of negative x, so say this is the negative x here, that sine value is the negative value of sine of x. So sine of x this way, opposite side of the x-axis. And for cos, it's an even function. So for a negative x value, you get the same y value as for the positive version of that x.